Hey there, folks. Welcome to another lecture in the Introduction to Earth Science with Dr. Matthew Wielicki. This is lecture number 2, Plate Tectonics. I am Dr. Matthew Wielicki. Thank you for joining. Today we're going to be talking a little bit about the history of plate tectonics and the implications of plate tectonics. The image you see in front of you is a nice cross-section of a lot of what we will be talking about today. And plate tectonics has essentially become the underlying theory in Earth science. It's what evolution is to biology, plate tectonics is to geology or Earth science. And if you would have asked scientists less than about 100 years ago what the planet looked like, you would have likely heard that the planet has always looked like it does today. There was really no way for scientists to try to imagine the mechanisms that would be powerful enough to move continents across the planet. And it was relatively assumed that since we didn't see large continental land masses moving around, that the planet has essentially been in a stagnant configuration, and the continents were always and remain where they are. And yet we know now today that that is in fact not the case. If we think about the Earth on the last day of the dinosaurs, 65 million years ago, we can see that the planet looked dramatically different than it does today. Particularly, there was significantly higher sea levels, so there were inland seas that don't exist today. Much of Europe, Western Europe, had not yet been constructed. India was an island and had not yet crashed into South Asia to create the Himalaya and the Tibetan Plateau. The Atlantic Ocean was significantly smaller, and the Atlantic and the Pacific were allowed to communicate as Central America had not filled in yet and made the isthmus that connects North America to South America. People had long been thinking that was it possible for the continents to move, because once humans had mapped the Earth's surface, it became pretty evident and apparent that the northwest and western the coast of Africa and the eastern seaboards of both North America and South America appeared to look like puzzle pieces. And so it had long been thought and imagined that it's possible that these were once together, but nobody really could find conclusive evidence to support that theory. Until a gentleman by the name of Alfred Wegener came along. He's a German meteorologist, born in the late 19th century, but did most of his work in the early 20th century. And as a scientist and a meteorologist at that time, and going on expeditions, many of these folks were kind of jacks of all trades. So Alfred Wegener was part meteorologist, part geologist, part paleontologist, and he was able to go on these expeditions and explore the planet. And he was really the first one to start making the observations that led eventually to what we accept now as the theory of plate tectonics. The 4 observations that Alfred Wegener made led him to a theory that he called the theory of continental drift, and it's essentially the birth of the theory of plate tectonics. Those 4 observations were what we just mentioned, the shape of the continents and the appearance that they fit like puzzle pieces. Paleoclimate data, paleo, the suffix there means ancient, so this is ancient climate data. The distribution of fossils and the distribution of similar geologic units or rock units on both the Americas, on the eastern seaboard of the Americas, and the western coast of Africa. So the first observation we already mentioned, that's the fit of the continents. Wegener thought that it just can't be by random chance that the coasts of North and South America and Africa appear to fit like puzzle pieces. He thought that this was clear evidence that they were once together. He coined the term Pangaea or Pangaea, which is Greek for all land or entire Earth, and that is the name that was given to the last supercontinent, Pangaea, that existed prior to the breakup and the formation of the Atlantic Ocean. The second observation that Alfred Wegener made was paleoclimate data. This was ancient climate data. And this was really regarding the distribution of plants on the planet and where we would have warm weather plants and essentially what would be determined coal swamps. We'll spend a whole chapter talking about energy resources and how coal is formed, but it's essentially the remnants of a swamp that has been buried and placed under heat and pressure such it becomes a sedimentary rock. And he realized that coal swamps would only exist in certain climates on the planet. And the planet is distributed into climatic zones. Because the Earth is on a tilt of about 23 degrees, the solar radiation moves back and forth around the equator up to the tropics and then back down south and never really gets all the way to the poles. And what that does is essentially makes the tropics around the equator much warmer than the poles. And Alfred Wegener was convinced that this climate state was relatively stable and that if he finds evidence of warm weather swamps, they must have existed somewhere near the tropics and that they couldn't exist near the poles. He also identified what we call glacial striations. So the image you see there is a mountain glacier, or sometimes referred to as an alpine glacier. These are large and thick, sometimes hundreds if not kilometers thick ice sheets that are moving down due to gravity. And all that mass, as it's moving down the valley, it picks up little bits of rock as it goes, and then it scours the surface. You can see the little inset image there and those clear scour lines. We call those glacial striations. And we think that that is clear evidence that at one point a glacier must have crossed over that rocky surface, because we don't know of another mechanism that would have enough force and enough mass to actually scour the rock like that. So glacial striations tended to be evidence of glaciers. And Alfred Wegener was exploring Africa at the time, and what he noticed was that Africa was essentially divided into deserts in the north and the south, so the north being the Sahara Desert and the south being the Kalahari Desert, with a rainforest in the middle that was straddling the equator, and savannas and grasslands in between those two. And in South Africa and in other places like southern India, what Alfred Wegener identified was glacial striations, and he realized that these areas today were at much too high temperatures to sustain glaciers. In fact, very rarely does it even snow. And in order to get a glacier, not only does it have to snow, but it has to be cold enough in the summer that that snow doesn't melt, such that you can pile up and create the pressure that will eventually create glacial ice, which will eventually create the glacial striations that you can see in the image in front of you. And because he was identifying these glacial striations in areas that were in the tropics, in warm weather climates, he realized that this is evidence that not only were the continents moving, but it appears that at one point in time, the continents must have been more concentrated near one of the poles. In fact, he decided, and it appears that it's correct, that they were concentrating near the South Pole. And because they were at such a different latitude than they are today, that allowed the temperature to be low enough such that glacial ice could form and eventually create the glacial striations that he was observing in places like southern Africa or southern India. He also noticed that there was coal deposits in very cold climates. The image that you see there is a coal deposit in northern Siberia, which is northern Russia, a climate that today is not very conducive to creating all of the plant life necessary to create a coal deposit. When we tend to think of coal, we tend to think of things like this and swamps, right? Swamp People is filmed in Louisiana. These are areas that are warm, they're arid, they have quite a bit of precipitation, they are very full of organic matter. If you ever go to a swamp, you'll see that there's a little bit of a smell to it sometimes. That's all of the organic matter that's decomposing. And it's all of this organic matter, all of this carbon that eventually gets buried and compressed into the sedimentary rock that we call coal. When we think about polar regions, we tend to think about areas that look like this. So this is northern Siberia. You can see that there is some trees around, but it's relatively devoid of the amount of organic material necessary to make a coal deposit. And so these types of environments are not very conducive to forming coal deposits. And when Alfred Wegener started to map where he was finding coal deposits, he found something very interesting. He found that many of the coal deposits were scattered around very cold climates. And again, this was more paleoclimate data, ancient data, that suggested to Alfred Wegener that these coal deposits signify warm temperature swamps. And because they are in latitudes that are now cold, that's evidence that the continents must have been moving around on the planet such that they were experiencing different climatic conditions for sufficient amount of time that coal swamps developed and eventually coal deposits developed. His third observation was the distribution of fossils. As a jack of all trades and a partial paleontologist, Alfred Wegener identified things like the mosasaur or the cyanoganthus. These are a mosasaur is a freshwater, shallow water reptile, and cyanoganthus are things that were like ancient cats and lions. They were relatively stubby legs. They appear not to be very good swimmers if we think about their body shape. Obviously, we've never experienced one in real life, but just by their body shape and their stubby legs and bigger body, we think that they likely weren't very good swimmers over long distances. And yet he was finding these fossils distributed across land masses that were separated by oceans. From South America to Africa, separated by the Atlantic Ocean, or Africa to India, separated by the Indian Ocean, thousands of kilometers of water. And it just didn't seem to be possible to him that these types of animals would have been able to swim. And so this was further evidence that the land masses must have been connected, and these animals were able to walk across the land, and thus their distribution of their fossils is found on land masses that are now separated by oceans. And the fourth and final observation, as partly a geologist, Wegener identified that the rocks, the lithology of the rocks, the characteristics of the rocks on both the eastern coasts of North America and South America and the western coast of Africa appeared to be very similar. It's possible that this is a coincidence and these rocks formed very similarly and very similar in age. However, he thought that that seemed to be a little bit out of the realm of possibility, and it was likely that these rocks formed simultaneously when the land masses were together, and then they were separated by some forces that pushed the continents apart and created the Atlantic Ocean. These four observations led Alfred Wegener to write his seminal book known as The Origin of Continents and Oceans. He was writing on the success of Charles Darwin and the origin of species. He really felt that he had discovered an underlying physical theory that explained a lot of how the Earth works. Unfortunately, the consensus at the time was that the planet was stagnant and that there was no possible force great enough to move such large masses as the continents. And Alfred Wegener was criticized by the scientific community, and he passed away in Greenland on an expedition in the early 20th century, and his theory essentially laid in dormant for a few decades until it was rediscovered later on by more evidence, and eventually was proven to be correct and became the theory of plate tectonics. And Extra bits of data that really brought Alfred Wegener's ideas back to light were paleomagnetism. So paleo again means ancient. So this is the ancient magnetism, and the ocean water depth variations, or how the seafloor looks, which we call bathymetry. Just a reminder from the first lecture, the Earth is essentially a dipole magnet, meaning that we have magnetic field lines that leave out of the South Pole and then enter into the North Pole. And this is why when you hold a compass, your needle will align with these magnetic field lines and point towards north. This is thought to be a result of what we call the geodynamo, which is rotations in the liquid outer core of Earth. And in the first lecture, we talked about the benefits of this magnetic field as it blocks much of the harmful solar radiation that would be reaching our surface if we did not have a magnetic field. And this is very beneficial to life on the surface of the planet. The magnetic north doesn't always line up with geographic north. In fact, the magnetic north, where the field lines are entering back into the planet, has been moving around with time. And you can see on this plot that it was moving around and got pretty close to the Arctic Circle in northern Canada at the start of the 20th century. And if you notice, it's been actually rapidly moving over the last few decades. In fact, some folks claim that this may be evidence of a coming reversal, but the magnetic north has actually been drifting more than it used to before. We call this polar wander, and the South Pole moves around as well. If you've ever done any sort of orienteering, you may have set a declination on your compass. This is due to the fact that magnetic north and geographic north don't exactly line up. And in a compass, what you're trying to do is find geographic north. And so what we do is we set a little bit of an offset, which we call a magnetic declination, onto our compasses, which will correct for the fact that magnetic north and geographic north don't exactly line up. And this will allow our compasses to point towards geographic north, which is really what you want when you're trying to orient yourself and find a way in nature. This magnetic field is very important because it also allows rocks and lavas that reach the surface and solidify to record where north is. And so if we think about a lava coming out on the surface today, it comes out as a liquid. That's the definition of a lava. It's a molten rock at the surface. We'll talk about that when we talk about one of the three rock types on the planet known as igneous rocks that form from molten rock, both magma that's within the crust and lava that's at the surface. If a lava flow comes out today, there's magnetic minerals inside that lava, the magnetic crystals, and those magnetic crystals will act very similar to the needle on your compass. And because it's in a liquid, they have room to move around, and so they will orient themselves with magnetic north. And as the lava cools, they essentially will be locked in place because now the lava will become a solid. There's no more room for these minerals to move around, and so essentially it locks into place where today's magnetic north is. And if we study this rock 1,000 years from now, we would have a record of where magnetic north was in 2023. Keeping that in mind, what we can do today is we can go and look at ancient lava flows, things that are millions, tens of millions, hundreds of millions of years old, and we can figure out where magnetic north was at the time that that lava was created. And that essentially leads to two possibilities. Either the magnetic north is wandering so much that it can almost reach the equators. Alfred Wegener didn't really think that was possible. They didn't really understand polar wander at the time, but really the assumption was that the planet's axis is relatively stable. We know now that the obliquity, or the axis of the Earth, does have some variation, and it does move around, and it also what we call precesses like a top. You can think of a top that's spinning and slowing down, and the top of it starts to kind of wobble. So we know that the axis of the Earth isn't totally stable, but it didn't seem to be plausible to anyone that that North Pole would be somewhere near the equator. The other option is that the pole is staying relatively fixed, and the continents must have been moving such that when we look at these lava flows from subsequent different lava flows that are on top of each other, and they're pointing at different directions, that could be evidence that the continent is actually moving across the surface of the planet. And as you move across the surface of the planet, north is not now in the same direction. The second real big piece of evidence that kind of brought Alfred Wegener's ideas back to the limelight was World War II and our development of submarines and the importance by the Navy to map the ocean floor. We call that the bathymetry of the oceans. It's essentially the topography of the ocean floor. Submarines have obviously Navy personnel inside them. They need to be able to move around in the depths of the oceans without fear of bumping into something. And so it became very important for the Navy to map the ocean floor such that they could be safe operating in the waters offshore and in the depths offshore, and not have the possibility of running into anything. They hired a earth scientist by the name of Harry Hess to help do this. They essentially do this through sonar. You take a Navy ship and you tow an instrument behind it that sends down sound waves through the ocean. The speed of sound in water is essentially constant, and so the time that it takes for the sound to go to the bottom of the ocean floor and then reverberate back up to the instrument tells you something about the depth of the ocean floor, and tells you something about how the ocean floor is undulating and whether it's relatively flat or there's mountains. And what scientists and Harry Hess found was very surprising. Prior to this work, it was assumed that the ocean floor would have looked like a bathtub. In that very bottom image, if you come off of the coast of South Carolina or Florida and you go due east all the way across to Africa, the idea was that the deepest part of the ocean would be in the center. There'd be a steady decline from each coast down to the middle, where that would be the deepest portion. And to their surprise, what they found was a large mountain range that stretched all the way up the middle of the ocean, which became known as the mid-ocean ridge. One other thing that was identified was that the crystals inside this oceanic crust near the ridge had a very unique pattern. They pointed in different directions, and some of the rocks were pointing north while some of the rocks were pointing south. Oceanic crust is essentially created by the intrusion of magma into a boundary that is pulling apart. So in that image there, you can see a little red in the center. That is new, fresh magma that's intruding into the center there, and then it's being split apart as new magma intrudes. And you can see this repetitive pattern of rocks that were pointing north and rocks that were pointing south. And this was a very big discovery because this suggested that at times in the Earth's history, North Pole was the South Pole and the South Pole was the North Pole, meaning there were times where instead of today, as the magnetic field lines leave the South Pole and enter the North Pole, the magnetic field lines were leaving the North Pole and entering the South Pole. So your compass needle would have actually pointed in the opposite direction. And we call this magnetic reversals. These have happened many times in the recent history. We don't fully understand the mechanism involved to make this happen, but we do seem to see that there was little impact in terms of the flora and the fauna that existed on the planet. However, we don't know what effects a magnetic reversal would have onto things like our electric grid or for example, our satellites that are in space, because the idea would be that the magnetic field would weaken severely as it's going through a reversal, which means we would be exposed to some of this high energy solar radiation that the magnetic field is blocking today. Harry Hess and his fellow scientists also noticed that the rocks around the mid-ocean ridge tended to be younger in the axis, so in the peak of the magnetic ridge, and then would get older as you went away from the peak in either direction. And so the youngest rocks were at the axis of this new mountain range that was discovered in the middle of the Atlantic Ocean, and it appeared that the rocks were getting older as you moved off to either side. And it was clear that there was a pattern to both of these. The ages of the rocks and these magnetic field reversals appeared to be equal and repeating on both sides of the mid-ocean ridge. There was a really distinct pattern of this alternation between reversals and the magnetic field, and each time there was reversal, on both sides, the rocks appeared to be about the same width and about the same age. A couple extra bits of evidence Alfred Wegener and his fellow scientists discovered was that the mid-ocean ridges were essentially devoid of sediment, and as you moved away from the mid-ocean ridge, sediment started to increase. This was further evidence that the rocks in the axis were the youngest, and then as you moved away, the rocks must have gotten older and older because it takes time for sediment to accumulate. The older and longer these rocks have existed on the sea floor, the thicker the sediment pile on top of them should be. And as they saw this progression away from the axis and the thickening of the sediments, this was further evidence that the age of the rocks was progressing as you moved away from the mid-ocean ridge. And finally, they realized that the ocean crust had a very different age than the Earth, or than the continental land masses per se. The oceans appeared to be much younger than the continental land masses. The continental land masses are on the order of hundreds and billions of years old, hundreds of millions and billions of years old. In fact, there's quite a few cratons that are 3 or 4 billion years old, approaching 4. The oldest rocks we have on the planet are just over 4 billion years old, although we do have minerals that date all the way back to 4.4 million years old. That's a lot of what I do, which we'll talk about a little bit more when we talk about the biography of the Earth. But you can see in the image in front of you that the ages of the oceanic crust were significantly younger. The warm colors there are in the reds are on the order of 0 to 20 million years, and then the cool colors all the way to the purples are on the order of 280 million years. And they realized that the oldest oceanic crust, the oldest rocks underneath the oceans, were significantly younger than the continental land masses. In fact, almost no parts of the ocean were older than about 250 to 280 million years. And this led Harry Hess to write a very seminal paper in the early 60s that he defined a concept known as seafloor spreading. And he had identified all of these bits of evidence that led him to believe that in this mid-ocean ridge, this mountain range that was discovered in the middle of the Atlantic, the crust was actually spreading and new crust was actually being formed. Harry Hess had the foresight to realize that that has major implications, that somewhere else on the planet there must be crust that's being consumed or destroyed because the planet wasn't inflating like a balloon. We knew that the distances of two locations on the surface were staying stable. And if you inflate a balloon, you put 2 dots on it, as you inflate that balloon, the 2 dots will start to move apart from each other. So the distance along the surface to get from those 2 points will actually increase. And we had been measuring distances for a long time, and we knew that there was no evidence that the planet was actually expanding, and thus there must be portions of the planet where crust is being consumed or destroyed, which we eventually discovered and we call subduction zones that we'll talk a little bit more about in a second. And so Harry Hess realized that the ocean crust is constantly being recycled. The reason that the ocean crust is so young as compared to the land masses is it is very active. It's being created while it's also being consumed, and it's in a very efficient process on geological timescales, such that the oldest crust was only a few 100 million years old in the oceans. And if we think about how this process progresses, we can think about, for example, Pangaea breaking up and the Atlantic Ocean forming, so that in that upper image at time 1 would be the eastern seaboard of the United States and the northwestern seaboard of Africa that were once together. They are now starting to separate, and new oceanic crust is being formed in the middle. The magnetic field lines are in a certain orientation, and thus the little magnetic crystals that are forming are being locked into that orientation. As this progresses, you can see that in time 2, things have started to spread a little bit more. We have a magnetic reversal, and the magnetic field lines are now in the opposite orientation, meaning that the little crystals that are being locked into the ocean crust are also in the opposite orientation. And as we progress to time 3, we're starting to see this repetitive pattern on both sides of this mid-ocean ridge that is essentially creating new oceanic crust and pushing apart the Americas and Africa to create the Atlantic Ocean. And this essentially was the birth of the plate tectonics theory, which states that the Earth's surface, the lithosphere, and the upper mantle. So the lithosphere is the crust and the upper mantle. We touched on that a little bit in lecture 1, but recall that when we divide the Earth into layers, we can do it chemically, where we talk about the crust, the mantle, and the core, but we can also do it mechanically. And when we divide the upper portions of the planet mechanically, what we see is that the crust and the upper mantle, which we call the lithosphere, it behaves in a brittle fashion. It has brittle deformation, meaning it's cool enough that it breaks and doesn't bend. And below the lithosphere, we have a layer that we call the asthenosphere that is in the mantle. And this is an area that is allowed to flow over geologic time. And so the plates essentially float, the lithospheric plates, the crust and the upper mantle, like you can see in the upper left-hand image, they essentially float on the asthenosphere. That's not totally correct, but it's kind of a way that you can imagine this occurring. The asthenosphere is by no parts, it's not molten by any means. It's not a liquid. It's just hot enough that it can behave more like silly putty or dough, and it can flow over geologic time, as opposed to the lithosphere that behaves very rigidly, and if it's deformed, it will bend or break and fracture essentially, as opposed to being able to flow. And so the plate tectonic theory was born, and Alfred Wegener was proved to be right. The continents do move. It's really that they are essentially passive. They're essentially on the ride, along for the ride, as the oceanic crust is really what's driving the motions of the continents around on the planet. That's something Alfred Wegener didn't realize. He thought it was really the continents themselves that were moving, almost like icebergs poking out of the crust of the Earth. But it appears that the main driver of this is in the oceanic crust, and you can see, for example, the North American plate. It's essentially the continent of North America, but also half of the Atlantic Ocean, and the motion that we're experiencing in the North American plate is really primarily driven by the mid-ocean ridge in the Atlantic that's pushing apart and creating a larger Atlantic Ocean, and continuing to separate what used to be the supercontinent of Pangaea. And it's really the interactions at the plate boundaries that are going to become very important, because that's where we're going to see that we have our earthquakes, our volcanoes, and, for example, mountain ranges. This is a pattern of earthquakes, and you can see it's not perfect. There are red dots that are essentially scattered around in lots of places, but as a general rule of thumb, the earthquake densities tend to follow along the plate boundaries. And that should make sense. It's where the plates are grinding past one another that we can build up the stress and eventually break into an earthquake. And we'll spend a whole chapter talking about the mechanisms of earthquakes. And so it's really the plate boundaries where all the action is, so to speak. The center of the plates are relatively quiet. I teach at the University of Alabama currently. We're really far away from any sort of plate boundary, and we don't really worry about earthquakes. Where I grew up in Fresno, California, I recall as a young student doing earthquake drills every year because we were close to a plate boundary, and thus California has a much higher risk of earthquake damage and earthquakes occurring than, for example, Alabama. So that's why we're going to focus on the plate boundaries. And the plate boundaries are essentially defined by the relative movements between the two plates. And there's essentially three types of motion you can have between two plates. You can have divergence, where the plates move apart from each other. You can have convergence, where the plates move towards each other. And you can have what we call transform boundaries, where the plates aren't really coming together or pulling apart, but they're essentially sliding past one another. And each of these plate boundaries has distinct geologic processes that we will discuss. I will be showing sometimes maps, and if you look at geologic maps, you may see these types of symbols. So I just wanted to show that a convergent plate boundary is usually denoted as a dashed line, a thick dashed line. A divergent plate boundary is a solid, thick line, and a transform boundary is a solid, thin line. You may see other symbols on maps, so I just included this here so that folks wouldn't get confused if they see these symbols on maps. So let's talk about a divergent plate boundary first. So divergence means that the two plates are pulling apart from each other. So this is what Alfred Wegener identified as seafloor spreading. You can see the arrows in the picture are pulling apart. Typically, these are found in the oceans, which we call mid-ocean ridges, and that's where they were discovered by Harry Hess and the Navy. This is an area where new crust is being formed. We term this a constructive plate boundary because we are constructing new crust. There is earthquake activity at these locations, and there is also volcanic activity, although the volcanic eruptions tend to be rather small. Here's some images of what the Atlantic mid-ocean ridge looks like. You can see in the lower right image that there is lava reaching the surface. However, that lava is being extruded at the bottom of the ocean, which is very cold and near 0 degrees Celsius, so that lava quenches very quickly. We don't see flows like we may think about, for example, in Hawaii, but it is very similar types of rocks that we see in Hawaii. We'll spend time talking about these types of rocks, but these are mafic rocks. The term mafic comes from magnesium and the Latin for iron, ferric. And so these are rocks that have a lot of magnesium and iron in them. They tend to be dark in color, and they tend to have a high density because both magnesium and iron are heavy elements. This is how these plate boundaries occur through time, very similar to what we looked at before. And it's this divergence, this pulling apart, that creates this repetitive pattern that Harry Hess was identifying on the ocean floor around the Atlantic mid-ocean ridge. Although they tend to be concentrated in the oceans, there are a few places where a divergent plate boundary is associated with a continental landmass. When it's associated with a continental landmass, we call that continental rifting. The most famous of location for this is the Horn of Africa that's pulling away from the mainland of Africa. This is known as the East African Rift Valley. I used to live in Somalia, which is basically right to the left of the R there in Rift Valley in Mogadishu, Somalia, and I had the pleasure of going out and seeing some of this Rift Valley. There's volcanism occurring. You can see these large valleys being created, and the theory is that in some amount of geologic time, that the Somali subplate or the Horn of Africa will have pulled away from mainland Africa, and there will be a sea in between, very similar to Madagascar that you can see in the whole picture of Africa. That's the island that has been pulled away from Africa in the lower right, and this will occur in some amount of time. One thing that we'll talk about when we talk about earthquakes is that earthquake activity tends to be concentrated on the western seaboard of the US. And we just mentioned that in terms of earthquake hazards. You can see in the little inset at the bottom image, that is what we call a seismic hazard map or an earthquake hazard map. Warm colors means more possibilities of earthquakes. Cooler colors means less possibility of earthquakes. You can see the warm colors associated with the western coast of the United States. However, there tends to be a few hot spots. In fact, one of these hot spots is right around the Tennessee, Arkansas, Kentucky, and Missouri border, and this is known as the New Madrid Fault Zone. This is actually the place where the largest earthquake ever recorded or ever noted in the United States occurred, the New Madrid earthquake. This was a very large earthquake. It happened in the 19th century, so we didn't have very accurate equipment to measure it, but it is thought to have been the most powerful earthquake to ever occur in the United States in recorded history. And in fact, there are reports of the Mississippi River flowing in reverse because there was so much ground motion that for some time the Mississippi River actually flowed in reverse. This is thought to be a failed continental rift. So when Pangea was breaking apart, it's thought that it tried to break apart here and it failed, and it eventually broke apart on what we have today as our eastern coast of the United States. But because it tried to break apart here, there's still quite a few active faults in the subsurface, and every once in a while those active faults will reactivate, and you will get earthquake activity in a zone that's relatively far away from the plate boundary. And so this is something we'll do a lot in this lecture series, is we'll generalize and put things into boxes because it's easier to explain. So earthquakes tend to be associated with plate boundaries, and that's absolutely true, but nature's messy, and there's always going to be exceptions to every one of our rules. So we kind of put things and discuss things as end members to overly simplify them, but we have to always keep in mind that nature's messy and there will always be exceptions to the rule. For example, the earthquake activity in the central US that's not really associated with any plate boundary. We'll move on to our next plate motion, which would be to come together, to converge. We call these convergent plate boundaries. When two plates come together, there will be one plate that sinks underneath the other plate, and that will always be the plate that has more density. So when an oceanic plate and a continental plate come together, the oceanic plate, by definition, is created from more dense minerals, and thus when these two plates come together, what happens is the oceanic plate will go underneath the continental plate. So one of the plates here will be consumed. We call this a destructive plate boundary. Again, earthquakes will occur, and also we have volcanic activity, including very large volcanic eruptions. There are three types of convergent plate boundaries depending on what the types of crust are converging. You can have an ocean and a continent coming together. You can have two oceanic plates coming together, and you can have two continental land masses coming together. So we'll look at each of these individually. As we mentioned before, when an oceanic plate and a continental plate converge, what happens is the oceanic plate will be subducted. That term essentially means pushed underneath. And as it's pushed underneath, it's pushed down into the mantle of the Earth. Because pressure and temperature increase as we go down into the Earth, this subducting oceanic lithosphere will be heated. Eventually, there will be melting that occurs. We'll talk about what type of melting that is when we talk about our igneous rocks that are forming from these types of processes. Those melts, because they are by definition hot and liquid, have a buoyancy force, and that buoyancy force will push them up through the crust. And usually where we have a oceanic and continental plate converging, we form what we call a continental volcanic arc. A good natural example of this is the Andes Mountains. The Andes Mountains are an active volcanic arc because the Pacific Plate is being pushed underneath the western coast of South America. As it's being pushed underneath the western coast, it starts to melt and it starts to create this volcanic arc. This is sometimes why you see Chile in the news, where they have large earthquakes and also large volcanic eruptions, because this is an ocean-continent convergent plate boundary. Another way of having convergence is having two oceanic plates come together. When two oceanic plates come together, we form what we call an oceanic island arc. Again, one of the plates will have to be consumed or subducted. The one plate that is consumed or subducted will be the plate that is older, because as it's older, it's colder. And so as it cools, it actually increases density because heat has a buoyancy force. So when two oceanic plates come together, the older plate will essentially be subducted. Again, as it's subducted and pushed down into the Earth, it will start to melt. That melt will rise because of its liquid nature and because of its heat, and it will eventually reach the surface. But instead of making volcanoes on a continental landmass, it creates volcanoes in an oceanic setting, which are volcanic islands. And if you've ever traveled around the Caribbean, you may have experienced some of these beautiful islands that are popping out of the Caribbean Sea and forming this beautiful island chain. They are great places to visit and to scuba dive and snorkel. But the reason that they exist is because a portion of the Atlantic plate is being subducted underneath a portion of the Caribbean plate. The Caribbean plate is relatively young as compared to the Atlantic plate, so the Atlantic plate gets subducted, and as it does, it melts, and thus we get this nice chain of volcanic islands that we love to go and vacation at. The last convergent plate boundary is very near and dear to my heart because this is where I spend a lot of my time in the field. This is a continent-continent convergence. This is where, for example, two continents slam into each other. The image that you see was taken from the space station. This is the Himalaya and the Tibetan Plateau. So on your left is the subcontinent of India. It's crashing in and moving to the right of your image into the southern portion of Asia. And as they collide, we create the largest mountain chain on the planet. And that's essentially done because both of the continental landmasses don't want to be subducted. So you can imagine at some time there was an ocean between India and southern Asia. It was known as the Tethys Ocean. Active subduction was going on, and it was bringing India up towards the southern edge of Asia. At some point, the two continents collide, and because continental rocks are made out of what we call felsic rocks, these are low-density rocks, neither of these land masses wants to be subducted or pushed underneath the other, and so they essentially crash into each other just like a car crash, where you have two hoods of cars, and what happens is they shorten in the horizontal direction, but they crumple and they thicken in the vertical direction. And so it's no surprise that in this type of setting, we have the tallest mountain range on the planet, the Himalaya, and the tallest mountain on the planet, Mount Everest. Here's another image of the Indian subcontinent slamming into the Eurasian plate, the southern edge of the Eurasian plate, and responsible for making the Himalaya. I spend a lot of time in Tibet, in the Lhasa region, trying to understand the evolution of the Tibetan plateau and uh, the consequences of this very tall landmass. These large mountain chains have global climatic implications. So this is some images from a field season a few years ago, and we're the upper left image. I'm sitting on a rock just below 20,000 feet. You can see we're almost in the cloud cover. It gets relatively cold at those elevations. The people are great, so had a lot of time spent chatting with folks and learning about their culture and about the way that they are protect their lands and the Buddhist religion. The upper right image is essentially what we do is we go out and we send back a whole bunch of rock samples. It's the rocks that tell us a lot about the evolution of the Tibetan plateau. So we get there and we find some folks that can make us these big metal boxes, and then we ship those back to the labs. So I was at UCLA. We did a lot of the work there at UCLA or at Cal Berkeley. And the lower image is a picture I took of one of these valleys. We would start from the valley where we would park the truck, and then we would climb up to the peaks of these mountains, and then we would sample rocks on the way back down such that we didn't have to lug the rocks around too much. We essentially replace our water and our food with rock as we come down, so we're always carrying something like 50 to 80 pounds on our backs. It's a grueling day's work, but it's really rewarding being in nature and in this beautiful landscape at these very high elevations. And after a few days, your body really does acclimate and you start to increase your red blood cell counts. And so we kind of hang out for a few days at the beginning just to get acclimated before we start doing these hikes. I was fortunate enough to spend close to 8 weeks in Tibet over 2 different field seasons. The final plate boundary that we'll discuss is a transform plate boundary. So this is neither convergence nor divergence. This is when 2 plates are sliding past one another. So no new plates are being created or consumed. So this is neither a destructive nor a constructive plate boundary. What we call this is a conservative plate boundary. And one important thing to note is that although earthquakes occur here, there's no volcanic eruptions that occur. The San Andreas Fault in California is essentially a transform plate boundary between the Pacific Plate and the North American Plate. That's why if you go to San Francisco, you have to be aware that there may be an earthquake event. However, you're relatively safe from any sort of volcano erupting and lava entering the city. Here are some images of the San Andreas Fault system. So the upper left is an image after the 1906 earthquake in San Francisco that we'll talk about a little bit more when we talk about earthquakes in general. You can see the offset of that fence after the earthquake occurred, but you see no vertical motion. The plates are really just sliding past one another. Where I grew up in the Central Valley, and you'll see a lot of rows of orange and orchard trees, for example, in the bottom left. And where the San Andreas Fault comes through, you can see that they are offset because the plate is constantly moving and we have this constant earthquake activity. The lower right image is from Hayward, California, where you can see that it's either really shoddy construction by the folks that made the curbs and the sidewalk, which it really wasn't. It's just a few decades old now, and because the plates are constantly moving, that the curb has now been offset by a few inches. But again, you don't see any sort of up and down motion, and there's no lava that's reaching the surface. We know now with modern GPS that the plates move about the speed that your fingernails grow, so on the order of about 3 to 7 centimeters per year. There's some that move remarkably slow on the order of less than 1. There's some that move remarkably fast up to something in the low teens. But on average, 3 to 7 centimeters per year is about a good number, and that's essentially about the speed that your fingernails grow. And so you look down at your fingernails right now, you don't really see them growing. That's why we don't really feel ourselves moving around on the plate, even though wherever you are on the planet, you are moving at some amount of centimeters per year as the plates move around. When we talk about the margins of the continents, we now realize that the continents are kind of along for the ride. They're not really the main players. It's the oceanic crust that's the main player. And so when we think about the margins of the oceans and the continents, we've divided them into active and passive margins. And the United States is a great example of that because the western seaboard is an active margin, and that meaning that when you go off of the continental landmass into the ocean, you are crossing over a plate boundary. While the east coast is a passive continental margin, because as you go off of the eastern seaboard into the oceanic crust, you are not crossing over a plate boundary. In fact, the plate boundary is many, many kilometers away in the center of the ocean in the mid-Atlantic ridge that we talked about before. So although we have modern day GPS to measure plate motions, what we'd really like to know is how plates have moved over geologic time. We've only had GPS satellites for a few decades, and over geologic time, we're much more interested to know how the plates have been moving over millions or tens or hundreds of millions of years. And one amazing feature of the planet that can help us do that is what's known as a hotspot. And a hotspot, we like to use Hawaii as our classic example of a hotspot. That's a location where at the base of the lithosphere, there's a lot of heat and there's a lot of melting. And we think that that melting and that heat is relatively stationary so that the plate will continue to move off that. And if you go to Hawaii today, what you'll see is that at the active volcano is in Hawaii. That's the big island of Hawaii. That's where you still have active volcanism. If you're in Oahu, or for example in Honolulu, you have no real risk of an active volcanic eruption occurring because Oahu has now subsequently moved away from the Hawaiian hotspot. But these hotspots are really important in terms of understanding how plates move over time. And we can kind of imagine that with this little cartoon. So in time one, we have a hotspot that, for example, could have been Oahu a few million years ago. And as it's moving away, we start to make the other Hawaiian chains. And by time period 4, we have a few volcanic islands that have moved off the hotspot that are no longer being actively fed by the hotspot, so they have no volcanic activity. And the island, the big island that is now above the hotspot, is where the active volcanism is. And so what we can do is we can date the rocks on Maui and Molokai and Oahu and Kauai, and we can measure the distance between them and the big island, and that will tell us something about the motion over the last few millions of years of the Pacific plate. And we can do this much farther past Kauai, because although Kauai is one of the last islands in the Hawaiian island chain, once you go past Hawaii, there's still a lot of seamounts. These are older islands that have now eroded below the sea surface, but we can go in with submersibles and we can date these islands. And even after the Hawaiian island chain, we have another seamount chain known as the Emperor Seamount chain. And this is going in a different direction and suggests that at some point, a few tens of millions of years ago, the Pacific plate changed in terms of its relative motion. It's essentially moving to the northwest right now, but it appears that tens of millions of years ago, I think it's on the order of about 70 million years ago, it appears that the direction of motion of the Pacific plate was more due north than its northwesterly direction today. We see these hotspots in other places like Yellowstone, for example. So we'll talk about volcanic activity, but Yellowstone is also considered a hotspot. and we can look at the trace of where Yellowstone's lavas exist to understand a little bit more about how the North American continent has been moving through time. Again, we'll come back to this a little bit when we spend a whole chapter talking about volcanic activity. So how do the plates move? If it seems that we have a lot of evidence that the plates move, and so what's really driving the plates? The original theory was that it was being driven by what we call convection. If you've ever seen a lava lamp, that's convection right in front of you. That's the light is at the bottom. There is these two liquids. There's water, and then there's this little thicker reddish liquid in there. As that liquid warms up, it has a buoyancy force. It rises, and then as it cools, it starts to sink back down, and you kind of get this cyclical motion. And that's essentially what's occurring in the mantle. The mantle is being warmed by the core, and it's rising, and then it's cooling as it gets near the surface, and then it starts to sink. And so it was thought for a long time that it was these convection processes that were driving plate motion. What we've now started to realize as we've gotten better at imaging the interior of the Earth, which we'll talk about how we do that, we use seismic waves, or essentially earthquake waves. The modern image of the planet doesn't seem to show these very distinct convective cells. So the new theory is that it's what we call ridge push and slab pull that is essentially what's driving the plate motion that we see on the surface. So ridge push is essentially the force that's driving the plates away, and this is primarily due to gravity. The mid-ocean ridge is high. It's a mountain chain in the middle of the ocean, so gravity is pulling it down and trying to bring it back down. And the slab pull is essentially the force of the plate as it's going down into the mantle. You can imagine, for example, I like to do a demonstration in class where I take a chain and I let a few links of the chain hang off a table and nothing will happen. And as you keep putting an extra link off the table, eventually the chain will start to move and it will start to speed up as it comes off the table, because more and more links now are off the table and are susceptible to the force of gravity. And this is similar to this idea of slab pull. And so we think that it's now ridge push and slab pull that are the primary forces that are driving the plate motion that we observe on the surface of the Earth. And this plate motion essentially means that the continents break apart and come together over long periods of time. We call this the Wilson cycle. This is the process that is related to the build-up and break apart of supercontinents. And Alfred Wegener identified Pangaea, but we know now that before Pangaea there was multiple other supercontinents. And if we think about Wilson cycles, the Wilson cycle allows us to predict what the future of our planet will look like. And so there is an image of at the top of what Pangaea looked like. That's 250 million years ago. And then as Pangaea broke up, we started to make the modern day Atlantic Ocean. The Pacific started to get smaller and smaller. And if we think about projecting 250 million years into the future, you can see that the Pacific plate is starting to disappear. Australia has raced up and crashed into Japan, and the eastern edge of the Asian continent. The western coast of North America is approaching both Australia and the eastern edge of the Asian continent as the Pacific Ocean closes and disappears. Well, that's all I have for you guys about plate tectonics. Please follow me at Matthew Wielicki on Twitter. And I have a Substack that I like to discuss about climate, and that's called No Climate Emergency at .substack.com. Please follow me there if you're interested in discussing climate. I will have a whole lecture series about climate. I wanted to do an introduction to earth science because we'll be talking a lot about interesting or complex concepts when we start talking about climate. And so it's good to have a foundational understanding of earth science before we get into that. If you enjoy this, please share it with anybody and everybody. If you have any questions, you can post them here on YouTube, or you can post them onto my Twitter account. I do my best to address any questions that you may have. And once again, thanks for listening and have a great day.